Well, let's go ahead and get started then. So a pleasure to have you all with again. I'm Joe DalSanto, Professor of Astronomy here at the College of DuPage, and I'd like to welcome you to our presentation on the Hubble Space Telescope. We've all probably heard of Hubble. We've probably all seen its pictures. Well, tonight I'd like to tell you all about the telescope itself, and then we will get to the pictures. We will absolutely see some of the spectacular pictures. Got to tell you, it's very difficult to try to choose some from the many, many thousands of pictures Hubble has returned for us. So you probably know the telescope's named after Edwin Hubble, a famous astronomer, but I'd like to start out by introducing you actually to two other people who were perhaps more important in its development. In the upper right here, you see a man named Lyman Spitzer. As far back as the late 1940s, Spitzer was proposing the idea of a telescope in space. Now, being very visionary in this regard, because we had not yet orbited anything into space just yet, and yet he foresaw that potential. Well, eventually that idea continued to be discussed. As you can see here, NASA approved it and Congress funded the telescope. Nancy Roman, who just recently died, was very key in planning, developing the telescope. Sometimes she took the name of the mother of Hubble. So we owe quite a bit to both of these individuals for today's Hubble Space Telescope. Originally it was called the Large Space Telescope when it was first proposed, not yet being named. And yet the idea was to, again, put a large optical telescope into space. As we'll see, it's very important to be in space to get above Earth's atmosphere. And the plan, of course, was to have various instruments that would optimize the telescope for various types of astronomy. So during the 1960s, 1970s, Hubble was developed and designed. You can see it's quite large here, 44 feet long, weighs 25,000 pounds. Imagine that, about the size of a school bus, roughly. Why that size? Well, it was designed to fit into the then being developed Space Shuttle. The Space Shuttle would launch this telescope. The Space Shuttle would service this telescope. So we have a primary mirror about 8 feet in diameter. For those amateur astronomers out there, that's quite big. 94 inches in diameter. And as we'll talk about, this is the finest mirror ever made, although it did have one problem we'll discuss. You can see in our diagram here, the instruments are actually behind the main telescope. The instruments are shown in yellow, and the main telescope shown there in front of it. You see, of course, the solar panels to provide electricity. Then there would have to be other components as well to make the telescope work, communications, power, those type of things, to make the space telescope a space observatory, fully functional. Well, by 1990, the telescope was ready for launch. Everyone was very excited, but you might know the story that when it was first launched here aboard the Space Shuttle and then deployed, there was a problem. So before I get into that, I do want to share with you a short video that gives you a little taste of what that excitement was about when it was deployed. I'll go ahead and share this with you, this clip showing the telescope being released from the Space Shuttle.
Discovery, go for Hubble release.
With the sea and clouds of Earth reflecting on its door, the great silver bird was released to soar in orbit 320 miles above us. Astronauts would return for regular house calls to upgrade and replace parts as needed. Soon, it would be sending images back to us. Would we discover other worlds like ours? Could we finally unlock the secrets of the universe? The whole world waited for Hubble to open its enormous eye.
So that's how the story begins. The operational mission of Hubble began, as you saw, there was a very gentle release by the Space Shuttle astronauts. Of course, it took a little bit of time for the telescope to be prepared for use. And initially, the controllers on the ground endeavored to focus the telescope. But you might know the story that there was indeed a problem. When those first images came down, they were not nearly what we had expected. Great care had gone into the design, development, testing of the telescope, but there was a problem, as we're going to describe, a problem that, of course, needed to be fixed. So let's take a look. The idea here behind servicing mission number 1 in 1993 was for the Space Telescope to be serviced as originally planned by the Space Shuttle. The idea was that one of the main instruments in the rear of the telescope would be removed and another special instrument would be inserted with corrective lenses. This was called CoStar, and this device, as you see in the lower right, was about the size of a refrigerator. So the Space Shuttle, as you can see there in the upper right picture, would be maneuvered to capture Hubble. Astronauts would, of course, leave, go out, and service it by replacing this particular instrument. Light from the main mirror would be directed through this instrument first before being sent to any other instrument in its corrected form. So again, you can see the image here at the bottom of them doing that. Future instruments would be designed with their own corrective elements already built in. And so eventually, CoStar could be removed on future servicing missions to the telescope. Well, by now you know the mission was a success, a dramatic success, and did restore Hubble's vision. Interestingly, the mirror had been made extremely smoothly, but it had been made to the wrong shape. And it was a very simple error that had been made in the test fixture that was used in testing Hubble, and so it was easily missed by the ground personnel. But through much time and effort and ingenuity and thought, again, NASA was able to develop a fix, and CoStar was the fix. Let's take a closer look. First of all, on the extreme left here, you see a picture of a star from a ground-based telescope. And it looks very blurry, very pixelated, so to speak, very low resolution. This is due to the distorting effects of Earth's atmosphere. No matter what we do from the ground, Earth's atmosphere will always have some effect on what we can see up in space. It's a little bit like if you were to dive down to the bottom of a swimming pool and try to look up, things would look very distorted, wouldn't they? Well, when Hubble was initially launched, you see the center image showing significant improvement. In other words, the stars are smaller and better, but clearly you can see on the right-hand image what had been expected and what was delivered after CoStar was installed. So what a dramatic difference. We see not only a much clearer view, but especially notice, if you will, the number of very faint stars that are now visible in the corrected image that are simply not visible in the other two images. So you can see the, again, huge improvement. Hubble able to see more stars, fainter stars, and clearly, ultimately, more distant objects as well. So what a dramatic difference. The telescope was brought to full operating capability to take advantage of its mission. And as we'll see, the results have been nothing short of spectacular. Here's a dramatic evidence of that. One of the earliest returned images of Galaxy M100 prior to the repair of the optics, and then after the repair, the uncorrected versus corrected version. Clearly you see the difference. While that might be considered a nice image from the ground, clearly it was not living up to Hubble's potential, was it? And yet in the right one you see a far clearer, crisper image of this particular galaxy. We see fine detail in its spiral arms, much smaller resolution in this object. So by 1993, then Hubble was at full operating capability. It had done some good science prior to that, but as we'll see, the best was yet to come. Now you'll recall I mentioned that there would be other servicing missions, and you can see here several of them. And I'll give you a chance to just glance through the slide and read some of the instruments that were replaced on Hubble. In 1997, the spectrometer and spectrograph were replaced, giving Hubble better capability there. In 1999, the 6 gyroscopes which point Hubble were replaced because they had begun to fail. The telescope requires 3 to point, and as these failed, they were getting close to the point where the telescope would not be able to point itself steadily and properly, so those had to be replaced. The guidance sensors, which also hold it steady, the main computer, the digital tape recorder, thermal protection. So again, you can see some not only improvements, but some required repairs. And again, this was actually planned from the start. This was not a surprise to NASA. They had planned well in advance to upgrade the telescope. That was one of the beauties of its design, was that it could always be maintained, refurbished, serviced by the Space Shuttle. In March 2002, Hubble received a new camera, the Advanced Camera for Surveys. It replaced what was then called the WIFPIC 2, the Wide Field Planetary Camera 2, and that provided a much wider field of view and much faster images to be retrieved from Hubble. This was the first time the telescope was actually turned off or powered down since launch. This was necessary in order to replace the power control unit and even the solar panels. Solar panels were now provided that gave more power with less size and more stability to the telescope, enabling it to point more accurately and in a much stable configuration. So I think this little overview gives you some feel for Hubble's beginning, some of the early servicing missions, but as we move through the first decade of the 2000s, Hubble continued to need servicing. Now you might recall that in 2003, we tragically lost the Space Shuttle Columbia. That shuttle was destroyed on returning to Earth, and there was grave concern about flying the shuttle anywhere other than the International Space Station. The idea being that if the shuttle in flying was again damaged, astronauts could at least stay on that space station until a rescue mission could retrieve them. And so there was great concern about ever going back to Hubble. In fact, the NASA administrator at that time made a decision not to go back to Hubble. Well, you can imagine that the astronomical community and the public didn't like that decision. There was a tremendous upswell of enthusiasm and support for another Hubble mission, for NASA to find a way. And so NASA went back and put great time and effort into considering how best to do that, and they did come up with a way to have one more servicing mission back to Hubble. This would be servicing mission 4. This would be the last mission to service Hubble. And so again, much thought was given to what things do we need to do if this is our last opportunity to service the telescope. So servicing mission 4, again, turned into a very, very aggressive, very challenging mission. You can see a number of things that were on the schedule here. Installing a new wide field planetary camera number 3, new cosmic origin spectrograph, the Space Telescope imaging spectrograph, repairs to a camera in space. This had never been considered or attempted, and yet the ACS, or Advanced Camera for Surveys, had failed. And so the thought was, while we're there, let's give it our best effort to try to repair that camera in space. And again, this was something that had never been considered or designed into the camera, so this would be extra challenging for the Space Shuttle astronauts. Again, being the last mission, they certainly wanted to replace all the gyroscopes, those fine guidance sensors, again, the control and data handler, change the batteries. It's kind of like taking your car and you might as well fix it all, right? Okay. So here you see an image taken during servicing mission number 4. This would be the most challenging mission attempted. And those astronauts trained long and hard and rehearsed very much everything they were going to need to do during that mission. So let me share with you a little video that tells you a little bit more about that historic mission. You probably know by now it was a success, but let's watch servicing mission 4.
It's our last shot. It's the fifth and final time. It's our last shot to extend Hubble's life and bring it to the apex of its scientific capability.
And we just have lots of things we want to repair on Hubble and upgrade on Hubble, and not a lot of time to do it.
And we're going to take up everything we can take up. And on this flight, it's about 23,000 pounds of hardware.
This is going to be a very exciting, complicated, and challenging mission. We have 7 brave astronauts who've made a conscious decision to risk their lives in order to continue the advancement of science that Hubble has begun. They're going to buy another 5, perhaps 10 more years of lifetime for this great telescope.
We've got a full plate of things to do. We've got major science upgrades that we're going to do, so we have 2 new science instruments that we're going to install.
We're going to put in the cosmic origin spectrograph. And this is, the fanciest spectrograph that's ever been put into Hubble.
COST plus Hubble together will be able to observe deeper across the universe than any other instrument of this kind has ever done before.
Well, we're going to install the Wide Field Camera 3, Hubble's new imager.
Wide Field Camera 3's discovery factor is about 10 times better than the current instruments that we have on Hubble.
One of the beautiful things about our new camera, the Wide Field Camera 3, is it will be capable of looking farther out across the universe and farther back in time and closer to the Big Bang than any other camera we've ever had on Hubble before.
We're also going to attempt 2 repairs of the 2 failed instruments on board Hubble, the Advanced Camera for Surveys and STIS.
ACS was inserted on Hubble in 2002. Before it died, it was the most heavily used instrument on Hubble. And STIS was our first black hole hunter, and it went on to do the first detection and chemical analysis of the atmosphere of a planet around another star. We want to keep on doing that kind of work when STIS comes back online.
And this will be the first time that we've ever done an in situ repair of science instruments, so this will be a big challenge.
In fact, there's 110 of these very small screws that we need to remove from the instrument in order to gain access to the board we need to replace. And in space, things float and debris is a real issue.
If we're successful in repairing these 2 scientific instruments that have failed, it will be a real triumph for NASA engineering and will point the way toward our ability in the future to repair instruments in space. We want Hubble to last a while longer as a spacecraft. And since this will be our last opportunity to go service it, we're going to do things like change out all the gyroscopes that help Hubble point. We're going to put in a new fine guidance sensor. I say a new fine guidance sensor. In fact, it's a refurbished fine guidance sensor. It's one that's been on Hubble before and been brought back to Earth, refurbished it. So it's a used fine guidance sensor, but first class. We're going to change out our batteries. Never put in new batteries since Hubble was launched.
We have some insulation repair work that needs to be done.
We're going to install a new outer blanket layer called a noble, which is a solid. It's not a blanket anymore. It's a solid sheet that will go over the blanket.
And we'll also be installing a soft capture mechanism on the aft bulkhead of Hubble that will help facilitate a future mission to Hubble, primarily for the purpose of deorbiting it at the end of its useful life.
The 2 repaired scientific instruments working in tandem with the 2 new instruments that we're going to put on board Hubble in this mission will enable scientists to tackle some of the most profound issues facing modern science, not just astronomy, but physics today. This, in my mind, means that when the astronauts leave Hubble after servicing Mission 4, it will be at the absolute apex of its capabilities. It will be better than it's ever been before.
Sounds pretty challenging, doesn't it? And it was, as they said several times. So what was the result? Well, it was a very successful result. I got one more clip here to share with you. I had the pleasure of meeting astronaut Grunsfeld and asking him, so what was that like to work on Hubble? And he said, very challenging. So here you see John Grunsfeld and fellow astronaut Drew Feustel removing with PIC 2 to replace
And the
it.
Wide Field Planetary Camera 2 is clear of the structure of the telescope, and now Feustel will be maneuvered by Megan MacArthur to the temporary stowage location along the left side of the payload bay.
Clear to go and take a look if you need to. Thank you.
John, if you want to pause for a second.
350 miles above the Sudan in Africa.
Thanks, John.
Thank you. Megan, you're clear to start aft.
Megan, copy.
The helmet cam view.
This is a lot lighter than it is in the pool. Are you clear? Yeah, John, I'm clear. Thanks. Okay, my mystery is solved. Which was? I was worried I wouldn't be able to open this lid.
Looks like it's opening easily.
Yep.
Drew Feustel at the ready with the handhold now, as looking through the handhold down at John Grunsfeld as he opens the protective enclosure, exposing the new camera so that Drew Feustel can attach the handhold. Again, the 4 twist bolts you see there on the handhold, he will attach those and then basically reverse course and take the new camera up to its new home, the location at the Wide Field Planetary Camera 2. A little bit bulky, time-consuming to get that bolt free, but it's out of the telescope, and the opening is clean and ready to support the installation of the newest camera.
The bolt that you heard mentioned was quite a challenge. Some of you that have done this kind of thing realize you try to remove a bolt, sometimes it doesn't come out. And so after extensive deliberation with the ground, the decision was finally made to break the bolt, to remove that camera, bring that back, of course, and install the new one. So the mission was not without its challenges, but the astronauts were up to the task, and we had the best Hubble ever, still doing outstanding science for us. So again, I think this gives you a little taste of what we've been through to get Hubble to the point. How about some pictures? Otherwise you'll blast me, right? So let's take a look at some of the spectacular results from Hubble Space Telescope. We'll start out in our solar system with a view of Mars, as we simply can't see it through most any other telescope. You see the dramatic detail here visible in the planet. Of course, you see light and dark areas. But notice, for example, in our diagram here, those brighter white areas over on the left edge, on the right edge, those are clouds in Mars' atmosphere. Its atmosphere is fairly thin, not very dense like ours, but here you see again a dramatic view of that. Notice too the south polar cap, very little polar cap at the north, but our best view really of Mars. And as I said at the outset, there were so many images to choose from, it was very difficult to pick just one. But to try to give you some idea more of what a typical view of Mars might be like, you see that much smaller ground-based simulation that I've provided there to give you some sense of how much better Hubble's views are of Mars. I wanted to pause just briefly on this particular pair of images. They might not look so exciting. These are 2 of the largest asteroids. This is Ceres and Vesta. And you notice these images were taken back in 2004, 2007. Up to that point in time, really no asteroid had been seen as other than a speck of light. And yet Hubble broke through that barrier and showed us these as small worlds. Now granted, they're still fairly fuzzy. We don't see a lot of detail. We only see some vague bright and dark markings. But if nothing else, it allowed us to precisely measure the sizes of these worlds. And note how Vesta is not fully spherical. We had suspected that might have been the case from ground-based studies, and yet this clearly showed us that a large chunk of Vesta was missing, which strongly suggested some type of major impact during its history. So Hubble again gave us unique, unprecedented views of these objects. Later on, you might know, during 2012 and 2015, these 2 worlds were visited by NASA's Dawn spacecraft, and yet Hubble's work had prepared the way, had given us much better views, but also much better positioning, so that that spacecraft could be optimized for its mission to these 2 worlds. Let's move on to Jupiter, largest of the planets. I always think this image, which I obviously selected, reminds me of an image from a nearby spacecraft. Perhaps you've seen the Voyager images or the Galileo images. And again, at the upper right, a simulated ground-based view. But look at the intense amount of detail that is visible here in this stormy atmosphere of Jupiter. We see the great red spot with a big black dot over it. That's the shadow of one of Jupiter's moons being projected onto it. And so that gives you some idea of the size of those moons, again, compared to Jupiter and from our perspective. Typically, a small, maybe backyard telescope, you wouldn't see the moon as a disk. You'd see it as a little point of light. But here, Hubble, again, clearly shows us tremendous detail. And so Hubble, as we'll mention, allows us not only to take snapshots, but to monitor a planet over time, watch the weather change, and discern, again, the dynamics of its atmosphere, which can then be used to model it or test models or evaluate models. So again, you see a very dramatic, spectacular image here of Jupiter. Let's move on to Saturn. As I just mentioned, we see Hubble here able to image Saturn over an extended amount of time. As Saturn orbits the Sun, it takes 30 years. Saturn's tipped on its axis. We're tipped on our axis. As we circle the Sun every year we come around, we see a little bit different view of Saturn, as you can see here. Sometimes, as at top, we see the rings appear almost wide open. But gradually, steadily, those rings appear to close from our perspective until, as you see at the bottom, they might appear almost closed. So this is not only interesting to see, but this has a significant effect on Saturn. And again, images such as these give us a global perspective. You might know we've had other discussions on the Cassini mission to Saturn not too long ago. And that, again, places those observations in context if we see the global view here from Hubble. Besides the fact that the pictures are just plain spectacular, are they not? Saturn might have been the hardest one of all to select images from. So I splurged and took another slide. And what I wanted to emphasize here, you see some subtle color differences, is the fact that Hubble has the ability to image at different wavelengths. It can look somewhat into the ultraviolet and somewhat into the infrared wavelengths and see differences on an object like Saturn that, again, reveal to scientists further information. These images are something that are relatively unique. While we can have other space telescopes, Hubble is our premier instrument to do this. And so, again, you see some very spectacular, fine detail that we can see even from Earth at a distance of over 900 million miles. Hubble's able to show us such clarity. The outer solar system beyond Saturn is, as you can imagine, even more difficult to study because of the great distances. As we move out now to the planet Uranus, understand that Uranus is at twice the distance of Saturn. So almost 2 billion miles, or 2,000 million. And at that distance, of course, Uranus appears very small from Earth. It appears roughly the size of one of Jupiter's moons. So imagine now the difficulty in studying it. Well, you can see some spectacular images here. On the left, we see again a sequence of 3 images taken over several years showing again something similar as we discussed, that Uranus appears to change its orientation from Earth because of its orbit and ours. And notice in this case, Hubble is actually able to image the rings of Uranus. Those rings are extremely dark, extremely faint. We don't normally see them unless we have Hubble. And so you see a spectacular view here of the rings and their orientation changing. As we move into 2007, you see them appear almost edge-on. The image had to be specially processed, but Hubble was up to the task to pick out the faint remaining bit of light there from those rings. On the right, an even better close-up taken a few years later, and you see there a very, very rare event that we were able to capture. One of the moons of Uranus is passing in eclipse in front of the planet, throwing its shadow. Only Hubble was able to give us that particular image. You see the Earth and Moon there for scale. So here especially do we see Hubble kind of showing its capabilities. This is an extremely difficult planet to study because of its distance, and yet Hubble, again, is up to the task. You see, again, a very typical view of it there at the top. Something similar is the case with Neptune. At the upper right is about the best I've ever seen it in my telescope, and Hubble has completely, dramatically improved our view, showing us even features within the atmosphere, such as various storms. I had to, again, only select a few here, but again, Hubble's been able to monitor the changes in those storms over time. So this allows us to learn about the weather on these very, very different planets from Earth. That gives us a much broader context with which to understand Earth's weather, Jupiter's weather, other planets' weather. We're getting a much broader view of how planets work by being able to study different types of planets at different locations in the solar system. Well, let's move on. Out of the solar system, here's a spectacular image that I'd like to share with you, taken of another star. Now, the light from the star has been dramatically removed in that black circle. They've kind of put back the position of the star, but what we're really trying to highlight here is this ring of material that you see around the star. This is the star Fomalhaut. You can see this in the autumn sky. It has a ring of material around it that we believe is forming planets about 20 billion miles across, so a little bit larger than our solar system. But we had long suspected these rings. Here Hubble's able to show one. Okay? Hubble's amazing clarity was able to show us. Well, careful analysis uncovered, you see in the insert, in the close-up view, a little dot of light moving around Fomalhaut. And as you can see, Hubble picked it out at 4 different dates. And even that short distance that that object traveled during that time told us that more than likely that was a planet around that star. So I got to tell you that way back when Hubble was being designed, developed, discussed, tested, there was a lot of speculation. Would Hubble ever show us a planet around another star? Well, the answer was yes. Here you see it. It may only look like a little dot of light, but understand the historic accomplishment this is to see another planet around another star, orbiting around it. They were able to determine its distance, you can see there. Orbits in 875 years, so it's much farther from its star than even Pluto, and yet here Hubble can see it. How about the stars? Hubble's been an incredible discovery machine when we talk about the stars. Let's start out with star birth, or star formation, so to speak. On the left, one of Hubble's most famous images, maybe you've seen this, called the Pillars of Creation. This is a region several thousand light years away where stars are forming. And this entire region is filled with much gas and dust. And in those dark pillars, stars are forming deep within them. You can see a few little small kind of pinkish dots, for example, here and here in that central pillar. Those are stars that are somewhat on the edge or on the outside of the cloud that we can see partially, but others are buried deep within it. You notice too, 1 or 2 much brighter stars here in the region, and these are very massive stars pouring out a lot of energy. That energy erodes away the gas and dust and basically clears it away in a way, as you see here, that opens up the cloud, allowing us to peer into it and see those stars. So here we actually see stars, very young, relatively speaking, being formed and being essentially released, so to speak, from their birth cloud. At the top right, we see something very similar. Here we have a whole cluster of stars that has just recently appeared and emerged, so to speak, from its cloud. And you can see again the sense of the cloud being dispersed off there to your right. Notice in the upper left we have one star in particular with what appears to be, again, a circular disk around it here. And if you can imagine the 3-dimensional view here, this star is shooting out energy to the upper right and to the lower left in what we now call jets of material. Young stars are known to do this because of their magnetic field. So here Hubble again, in an unprecedented way, is able to show us something we'd never seen before. We'd strongly suspected with our best theories. And so here's where Hubble allows us to do cutting-edge science to essentially prove or disprove our theories based on the visual evidence. So what a tremendous view of stellar formation here provided by Hubble. How about star death? Stars last a long time, millions, even billions of years, depending on their mass, and yet ultimately they are going to run out of energy. So let's talk about these beautiful images. Maybe you've seen some of these. These are called planetary nebulae. And planetary nebulae result from relatively lower mass stars. They're changing elements within them to produce energy. Some of you are familiar with hydrogen to helium fusion in the core of a star provides the energy, but gradually that hydrogen is changed and consumed. And so ultimately you're going to run out of hydrogen eventually in the core of your star. Well, at that point the star is going to go through some changes. Believe it or not, even though it's run out of fuel, it's going to expand. It's going to expand and go through some changes. I won't go into great detail, but ultimately it's going to expel its outer layers out into space, and what will be left will be just a very small, very dense, very hot core of the star. And you can see that in these 2 images here clearly. Well, that very small, hot, dense core is so hot that its energy now is going to light up that cloud. The energy, especially ultraviolet radiation, is absorbed by the gas. The gas now re-emits it as visible light that you and I can see there. So again, Hubble showing us our best images yet of these particular images. We had certainly seen them before, but it gives us exquisite detail. And you see, they don't appear necessarily simplistic, do they? The one on the right gives you the sense, certainly, of kind of a spherical shell. Perhaps we're looking into the shell there. But on the upper left, you notice a little different structure, don't you? What we call morphology of this object. In other words, almost appears to be maybe some spiral structure or some inner shells and outer shells. So Hubble provides us the information to, again, analyze, evaluate, theorize about these objects and compare that to what we currently know. And so here again is where Hubble's power enables us to do, as we said, cutting edge science. Even the beautiful colors you see here are telling us something. These often indicate different elements. And that as well can take us back to compare to our understanding of our theories of how the star's been changing. So again, these particular images give us quite a wealth of information, besides being very pretty, to put on your computer desktop. Here's yet another example of a planetary nebula shedding its outer layers. And again, you get a sense here, this is a bit more of an energetic expulsion of material, and that's the case here. This is a very complex particular object, is why I highlighted it. And again, as it mentions, the Hubble data suggests not only gravitational, but even magnetic forces at work. We don't still fully understand these objects. There's much to be learned. But by having this exquisitely detailed images such as this, Hubble is allowing us to press forward, to press further, to learn more about these objects than we can simply from Earth. And so again, you can see the power, the capability of Hubble here, as I'll continue to say, showing us these different objects in all their beautiful forms, but there's an awful lot of good information here for scientists to be able to use and analyze. An even more violent fate awaits stars of higher mass. These objects, when they run out of fuel, collapse inwardly. Gravity will cause them to dramatically collapse inwardly. Well, as that material is rushing towards the center, it's getting denser and denser and denser. It's moving faster and faster. There comes some point when that very center of that star becomes so dense, incredibly dense, as we've discussed in previous lectures on black holes, for example, that the infalling material will literally bounce back off of it. It will bounce back off it very much like if you took a golf ball and threw it at a brick wall. That would come bouncing back at you, wouldn't it? And so imagine now unimaginable amounts of material at unimaginable speed falling inward and bouncing off this incredibly dense object. Is going to blow outward as a supernova explosion. This is one of the most famous ones we've studied. It's called the Crab supernova. And early humans saw this in the year 1054. They noticed a bright star in the sky. Of course, they didn't know what it was. But today we can pinpoint that spot in the sky that they saw and find this object. Hubble's enabled us to measure its expansion rate. And since we know the velocity at which it's expanding, and we know the size of the object, we can, in a sense, wind the clock backward and pinpoint how long ago it exploded. Guess what date we come up with? 1054. So the point is, again, Hubble shows us here in more detail this object than we normally see with other telescopes. Yes, we had been studying it prior to Hubble, but as you see here, exquisite detail in these filaments and tendrils. Hubble gives us an even more precise view of these things. And you can see especially the outer regions, kind of the yellowish, orangish filaments of material. But I'll just touch briefly on that inner bluish region. Extremely energetic, really, really high energy radiation in that region. So the Crab Nebula is a very, very well-studied object, and for good reason, because it tells us a lot about how stars die, especially stars of higher mass. Here's another image that up until just recently was only possible using Hubble. This is a supernova in another galaxy. Now it's one of the nearby galaxies called the Large Magellanic Cloud. This occurred back in 1987, and it's been, again, a very well-studied object. You see there a bright ring of material I'll highlight. This is where the powerful shock wave from the supernova has been expanding outward through some material that had been previously expelled by the star. And so this powerful energetic shock wave, as it's rushing outward, very much like sweeping up material as it goes, imparts tremendous energy to it and lights it up for Hubble to image here. You even see some very faint outer rings. They're just barely visible there up near those two brighter stars. So again, this is a unique capability that Hubble gave us a few years back to be able to image this thing in such exquisite detail. And as I said before, again, be able to test our theories, evaluate our understanding of what this object should have been like. We learned quite a bit from this object that we didn't know before. We had a certain basic understanding of what we thought supernovae were like. Well, Hubble observations helped us to revise and expand our understanding, and that's exactly why we do science, isn't it? To revise, improve, increase our understanding using tools such as Hubble. So again, you see the tremendous value of such an impressive tool. Let's move out of our Milky Way to other galaxies. I couldn't help but select this famous image of NGC 1300, just an exquisitely beautiful structure. And when you consider its size, tens of thousands of light years, it really does boggle the mind at how such a beautiful structure can be maintained over these sizes. We know, of course, natural laws basically sculpt such a structure. And yet here is where we still have so much to learn. Galaxies are extremely complex topics, and yet Hubble, again, as I've said so far, giving us our best, most clear, most detailed view. Notice that central kind of yellowish region there where we have some older stars. And then as we move out into the beautiful spiral arms, they take on more of a blue tint, don't they? Well, that blue tells us that that is stars of higher temperature compared to the stars in the center, more of that yellowish temperature. And so that tells us that these stars have to be a little more massive than the stars in the center. And as I just touched on briefly, that tells us that these more massive stars in the spiral arms are not going to live as long as the stars in the center. So you can see how, again, even something as simple as the subtle colors of an image can tell us something about the galaxy. In other words, those central stars in that central bulge region are older stars, older lower mass stars that are not burning up their fuel so fast as those hotter, more massive, bluer stars in the spiral arms. You see, too, if you look closely, some regions where there is some areas it might appear the stars are sort of missing. They're not necessarily missing in some of these areas as it is that there is dust present in the galaxy. What's the importance of the dust? The dust is part of the raw materials for new stars. So this does make sense. This fits, doesn't it? If this galaxy is showing us these beautiful blue spiral arms of relatively younger stars, that's because it has the raw material to make stars, doesn't it? It has the dust. Can't really see the gas that's necessary as well. But the point is, the picture takes on more meaning when we start to understand and analyze what we're seeing there in a bit more detail. And as I keep saying, Hubble allows us to do that better than with most any other telescope. Let's zoom into a few other ones. On the left is a relatively nearby galaxy, but it's of an unusual type we call an irregular galaxy. This is a relatively small dwarf galaxy, and up till Hubble's time, we had not seen it very clearly. It was a relatively small fuzzy blob. Well, Hubble basically uncovers it in all its exquisite detail. Once again, you see more of a predominantly bluish tint to this galaxy, as we just described. That indicates somewhat higher temperature to the stars, which indicates somewhat higher mass to the stars, which indicates somewhat younger age to the stars, implying that star formation must be going on in this galaxy. Where do we see that? Well, look closely at some of the small kind of pinkish regions you see in this galaxy. Here is where the gas and dust is coming together to form new stars. We saw earlier a few examples of that, those pillars of creation. Here is something similar in this galaxy. On the right, we see a variety of galaxies, don't we? We see a large dominant elliptical type galaxy with a very smooth type of light distribution. This is a large massive galaxy. Again, you note the kind of yellowish color, indicating the older lower mass stars. And yet you can see that it is attended by a number of others. one particularly prominent spiral in the lower right, another one just below the main galaxy. So the point is we have a group of galaxies here, and great variety. Much to learn by studying them in comparison to each other, especially in a group. As we're going to see in just a minute, galaxies often interact. And so we'll talk about that as well as we go on here. Here's a couple examples. Dramatic images taken by Hubble. At the left, we have what appears to be two galaxies caught during collision. We have the vertical, long, kind of flat disk shape of a typical spiral galaxy, but almost shooting straight through the middle of it is a very elongated, smooth distribution of an elliptical galaxy. And so we think that's exactly what's happening here, is that we managed to capture one galaxy basically shooting right through the other. Imagine that Hubble was able to give us this exquisite detail. We can measure the motions, the velocities of these objects, and again understand what we call the kinematics of the encounter between the two objects. At top, we see something similar, what appears to be more of that broad, roughly spherical elliptical galaxy, and yet this time we have a dust evident in a disk, don't we? And so might this be, again, a galaxy that has resulted from two galaxies merging together, perhaps an elliptical and a spiral, where the spiral would bring along its dust. But what was intriguing about this particular image, as you can clearly see, is the warp to that dust lane. The warp. In theory, most galaxies that are of spiral nature would have a relatively flat disk, and it would be very much in one plane. Well, clearly we don't see that here, do we? We see instead a tremendous warp. This also strongly suggests that something out of the ordinary has happened. Clearly there had to be some immense, colossal amount of gravity to warp this disk. So again, we can go in and measure the velocities and motions of the different parts of the galaxy and try to untangle that. Makes for fascinating science to try to understand how this could be. But when you see a simple picture like that and you see that warp, that's how scientists' minds go. They tend to think in terms of, well, what would cause that? How have we been able to measure those motions and maybe evaluate different theories about what's happening here? But I emphasize again, Hubble is able to show us this in such detail that we can do that work. We might be limited by other telescopes, but Hubble allows us to see that. Other encounters and even collisions of galaxies have been captured by Hubble. Now understand that, again, these are enormous, enormous objects. Galaxies, we said, are many tens of thousands of light years across, containing billions of stars in some cases. So you can imagine if we have two galaxies moving through space, it's going to take some time for them to encounter each other, isn't it? And here again, Hubble's been able to show us two different cases. Let's start out over on the left here with these two galaxies. They appear to be relatively what we call coplanar, in other words, both tipped approximately the same to our line of sight. Notice, if you look carefully, of course, the similarities between the two spirals, but notice how the larger spiral to the left appears to be silhouetting its outermost arm in front of that smaller, more distant galaxy. So that in itself gives us a three-dimensional perspective on this. It turns out that other galaxy is slightly behind the foreground galaxy, and that's why they've not distorted each other quite so much. In other words, they're not so much in physical contact in this case, but here you have one galaxy a little bit behind the other galaxy, and they're able to maintain their shape a little bit longer. It does highlight, again, clearly what I mentioned, the dust in this foreground galaxy to the left. That's not normally very visible. Well, here it is because it is silhouetted from behind by the second galaxy. On the right, though, we do see something even more dramatic, perhaps, and that is two galaxies virtually in contact, virtually in collision. You can imagine the tremendous effect this will have, the tremendous forces that are going to be involved. Now, generally speaking, there's going to be very, very few collisions of stars. Why is that? These look like very substantial galaxies. Well, remember, the space between the stars is enormous. If we were to take a model of our sun, perhaps 100 feet or so in diameter, something like that here in Chicago, the next nearest star would be many hundreds of miles away. probably out near the west coast. So there's a lot of space between stars. And so as galaxies do merge and collide, the stars tend to move through each other. There may be a very, very rare collision, but we think it's just that very, very rare. On the other hand, what we do see is tremendous gravitational interaction. Imagine now the gravity of hundreds of millions of stars all pulling on each other at different distances, different orientations, different velocities. This is why astronomers like supercomputers, because it's an incredibly difficult problem to solve. We've been able to model now, I think the latest model is up to maybe a few million stars is our best effort, and that takes quite a bit of computing power to actually try to simulate such a thing and model that. But I'll say it again, Hubble is allowing us to examine and to analyze real-world examples here as these objects do collide. We're able to take an image like that and go back and try to simulate that. Can we build a model that shows us this? And in many cases we can. And so that gives us confidence we're on the right track of understanding what's happening here. Other galaxies either have already collided or are not going to completely collide, but rather interact with each other. What's happening here is two galaxies, again, as I just described, their gravity is affecting us greatly, and they're literally wrenching stars out of each other, stripping stars out, drawing out long tails of stars that you see here from each other, distorting each other's shape dramatically. Again, imagine the incredibly powerful gravitational force to do that over tens of thousands of light years. Often what will happen is that as stars are again stripped out of one galaxy, they'll be flung out into space. Some might be captured by the other galaxy, but some might be flung out of both galaxies to wander out into intergalactic space. Sounds rather lonely, doesn't it? To be lost from your galaxy. These two in particular we've modeled exquisitely well and been able to reproduce both of these quite well. Up in the upper right here, this particular one is a famous example showing how those galaxies interact at various angles and distances and velocities. And if we have the right perspective, we can model what's exactly happening there. So this was one of the earlier examples that Hubble was able to show us that we've been able to model and understand relatively well. So again, I keep saying Hubble enables us to do that cutting-edge science, doesn't it? But let's look inside. What happens when galaxies do collide? On the left, you see a ground-based view. And you notice, as we described a minute ago, these long tails of stars are drawn out here to the top and bottom. But from the ground, we really don't see inside the two galaxies very clearly. Well, as you can imagine, this is where Hubble comes in. Hubble close-up view shows us the details of what's happening. So let's talk through this for just a minute. Number one, you've got two galaxies merging here, both not only with a lot of stars, but remember, often with gas and dust. Now the gas and dust often will form into large clouds, maybe several dozens or even hundreds of light years in size. Well, these clouds can collide. We said the stars tend to pass through each other, but when you have clouds of several hundred light years, several thousand stellar masses colliding, things happen. What happens? Let's take a close look. You can see in the close-up, you see kind of these two orangish yellowish regions. These would be those central bulge regions with those older, lower mass, cooler stars. So that kind of identifies for you where the two centers of each galaxy were, but notice the tremendous blue regions here and the tremendous dark, dusty regions. This is all a very, very complex region where these clouds are colliding and forming new stars. How do they form new stars if they collide? Well, think of the two clouds again colliding. They're going to compress each other. And as the density increases, that enables star formation. Gravity is now able to start to take that material that's of higher density and form new stars from it. And so the point is, when galaxies collide, we often see strong, vigorous bursts of star formation. A typical galaxy like the Milky Way may form, on average, perhaps one star per year, something like that. But here you can have a rate of 10 or more times that. So it still might not sound like a lot, But add that up over a few million years, that's a lot of stars that are being formed during these galaxy collisions. And again, as we mentioned earlier, you can see those regions are very bluish, indicating very higher temperatures, higher mass, younger stars. So once again, Hubble allows us to peer in here, see the intricate detail of these collisions, enables us to step back again and try to model that, or if we have an existing model, to evaluate it, to improve it, to update it, or maybe in some cases to discard it. But Hubble enables us to look and see as never before the details here of galactic collisions. So it's really been a powerful, powerful tool for us to do that. Hubble's shown us even more. Here we have a view of quite a number of galaxies. You're probably familiar with galaxy clusters. And you see over on the right one strong cluster, a little bit weaker one on the left. Notice, if you will, surrounding some of these are these long, thin arcs of material, such as here in the upper right, here towards the center. And notice how they are roughly in a circular pattern here. So this is a very mysterious clue for us, but scientists can use our theories, such as Einstein's theory of relativity and others, to interpret what we're seeing here. What's going on? Well, these galaxies have clearly a lot of mass. Hundreds of millions, billions, perhaps tens of billions of stars of mass, and probably that much gas and dust in addition. But you may have also heard the terms dark matter, matter we can't see. All of this matter, whether it's stars or gas or this mysterious dark matter, has gravity. And that gravity, according to Einstein's theory, will literally bend light. So what we're seeing here is something very profound. Those arcs of light you see there are not physical objects, but those are the distorted images of galaxies behind this cluster of galaxies. That light has passed through the galaxy cluster and been distorted into these arcs. So we are literally seeing an example here of gravity bending light according to Einstein's theory. And that's a pretty remarkable thing, isn't it, to be able to say that and see that. But scientists can take that one step further. We can turn that around. And understanding, again, how Einstein's theory describes gravity, we can now take that and say, well, if we know how gravity works, we can measure the arcs and their distance from the center. In other words, how much have they been distorted? How much have they been bent? Is it this much or this much or this much? And we can work the problem backwards and say, well, then there must be this much mass in the cluster. In other words, it would take this much gravity to bend the light this amount. Well, that much gravity requires this much mass. Okay, great. That's an interesting problem. The final step would be to say, how much mass do we see there? And we can get a pretty good estimate by looking at the particular galaxy and say, well, it's this big, it's this bright. We can make a good estimate of its mass in visible matter. And what do we find when we compare the amount of visible matter we see with the amount of total matter evident from the gravity? They don't match. This is how we know there's dark matter there. This is how we identify it. This is how we study it. By looking at these gravitational arcs of light and saying, well, clearly there must be this much mass there, this much gravity there. There's something there we don't see. So as you know, that's another whole topic. We'll have to have another lecture on dark matter, won't we? So gravitational lensing. We saw it some years back, but at first it was extremely difficult to see until we launched Hubble. Hubble's been our primary tool to show us this. In fact, Hubble's taken us even one more step further. Not only, in some instances, do these gravitational lenses show us those distorted images of a background galaxy, but in some rare cases, they will literally magnify, or so to speak, increase the visibility of that light of objects that we would never be able to see unless it was part of this gravitational lens. So Hubble, again, has given us just an unprecedented, very unique capability to see ever farther than perhaps we could. And scientists have taken advantage of that. They've pushed Hubble to the limit. And they have used it to do some extraordinary things that time doesn't allow us to go into great detail on. Well, this may be the ultimate Hubble images. Perhaps you've heard the Hubble deep fields. There have been several now. The original deep field on the left there, taken back in 1996, was just historic. Astronomers said, well, let's do this. We have this new telescope, new capability. Let's see what it'll do. And so they picked a blank spot in the sky and said, let's just leave the telescope pointed there for days and days and see how deep we can see. You can see the result here. It was many billions of light years. Some of those larger galaxies you see to the top, those are in the foreground. But if you look closely at that image, just about every little smudge of light you see in this left-hand image is a galaxy. It's not a star. There's only very few stars. I always tend to miss them. I can't even pick them out. But nearly every little smudge of light you see here is a distant galaxy that Hubble saw. So this was our deepest view at the time. It gave us a first good estimate of perhaps how many galaxies there might be in the universe. In other words, if you just look at one small area of the sky and you find, let's just pick a number, 1,000 galaxies, and you know how many square areas there are in the sky, it's not too hard to add them up. And our first estimate was somewhere in the range of about 100 billion galaxies. Now again, recall, galaxies generally have billions of stars. Thus the term, billions and billions. A few years later, Hubble was taken and used again, this time with the improved camera of the ACS camera, the advanced camera for surveys. Let's take another Hubble picture, the ultra deep field. Similar idea. Look as far as we can, as long of an exposure as we can. What will we see? Often that's the very first step in science is let's see what we can see. Let's see what's out there, right? Yet again, you see very few stars at all in that image. Every little speck of light. There, I finally found one. Here's a star in the foreground, and that's about it. Every little speck of light's a galaxy, billions of light years away. You probably also remember that billions of light years distance means that we are looking back billions of years into the past. In other words, that light has taken that long to reach us. Light travels 1 light year in 1 calendar year. So if you see a galaxy and you determine its distance at, let's just say 10 billion light years, that light's been traveling through space for 10 billion years. Now that's old light, ancient light, primeval light, whatever you want to call it. But isn't it a profound thing that Hubble can do for us here? It's a tool, but what we can do with it. I've often called astronomy an adventure of the mind. Well, here I think it is right in front of you. Isn't that just an intellectual adventure to think about what's out there, what we can see, what mysteries we've only begun to comprehend, much less understand. So you can see, I think, the value of a tool like Hubble. It's been a groundbreaking tool. Look what we've done with it. Some very smart people have found such ingenious ways to put it to use and have just achieved such impressive results using the Hubble Space Telescope. So let's see if we can step back, kind of step back and say, so what were maybe the major ways that Hubble's changed astronomy? Well, I came up with a few. You saw really some of our best views of the planets in our own solar system, short of sending a spacecraft out there, which is not trivial. How about those stellar nurseries, where we saw disks of material around stars, where we saw young stars emerging from their birthplace? Hubble gave us our best data there yet. Hubble showed us our first extrasolar planet. Again, a very profound discovery, isn't it, to know that those planets are out there. We saw galaxies in all their majestic splendor, their shapes, their sizes, their forms. We began to see some of their interactions. We began to find evidence of something unseen dark matter. So think of the rich, rich discoveries Hubble has enabled us to find out. We talked about the deep fields, how far out into the universe we can see. There's so much out there for us to explore. Hubble's even been used to give us our best, most precise determination of the age of the universe. How to do that? Well, just very briefly, it's given us our best precise distances to galaxies. And if we measure the brightnesses of very special stars, those stars can give us an indication of how the universe has been expanding, what rate it's expanding. Is it this fast or this fast or this fast? And that allows us to put a number on the age of the universe. So again, we now know the universe is just about 13.8 billion years old. And again, that number comes to you courtesy of the Hubble Space Telescope. Dark matter we mentioned, even dark energy. We didn't get into discussing that tonight, but the point is there's so much out there. I don't know, if I had to pick one, it's tough, but I might even go with number 7. Because think of how all of us have enjoyed seeing these Hubble images. And I hope I've been able to share with you a little bit of the science behind some of them, a little bit of the understanding. I can assure you that scientists have always been ecstatic with the capabilities of Hubble and its ability to do, as I said, cutting-edge science, allow them to do things they can't do anywhere else, and thus the immense value of the Hubble Space Telescope. So I think it's fair to say that Hubble has been the single most important telescope ever. That's a lot. But if I had to pick one, I think I'm going with Hubble. Because you've seen just a little sampling of what it's done for us. The clearest, sharpest, best views we've had of virtually anything we pointed at have enabled us to do science we can't do in any other way. Unfortunately, as they say, all good things must end, so Hubble's not going to last forever. It's really been doing a tremendous job. Think of it. It's almost 29 years old. There's a lot of us in this room that might not be that old, right? So what's the future? Well, again, they've been able to keep Hubble going until now, and it's going strong. Just recently, there was a small little glitch. They overcame that. Hubble's back in action. But what's ultimately going to happen? Well, you heard a little hint about it in one of the videos. They did attach a special device to Hubble. At some point, Hubble will need to be deorbited, and we want to do that, of course, in a controlled way. This is a large telescope, and it's not going to burn up completely when it comes down. So we'll want to be able to steer it to a safe plunge, perhaps into the ocean, where it won't cause any harm. But, as you might also know, Hubble's successor is being developed. The James Webb Space Telescope, you see in the lower left, much larger than the Hubble Space Telescope. Instead of a 2.4 meter mirror, we'll have a 6.5 meter mirror. And James Webb will be optimized to do even more infrared astronomy than Hubble. Notice it will not orbit the Earth. James Webb will be placed, as you see at the extreme right there, at the L2 point. Why there? This is a point where the Sun and Earth's gravity allow the telescope to float in a stable position. But why so far from Earth? 1.5 million kilometers. Because it can be free of the distracting influence of the Earth. Even Hubble today has to wait while it passes into the sunlight to do any observations to get back to the other side. It also has the heat of the Earth to contend with to some degree, and a few other things. And so this will be a better location for our next generation space telescope to be. Of course, there is that concern that we really will not be able to service it as we have been able to with Hubble. You can see James Webb has been tasked with very ambitious goals. Search for the light for the very first stars after the Big Bang. Hubble's taken us back to roughly, I'll just pick a round number here, 500 million years after the Big Bang. We'd like to look back even further and see those very first stars to again understand it, to test our theories, evaluate our ideas. James Webb will be optimized to do that. How about the formation and evolution of galaxies? Well, that's where they began, is in those first 500 million years of the existence of the universe. Hubble's given us just a tantalizing glimpse. We want to see more. We want to do more. And that's where James Webb will come in. How about the formation of stars, planetary systems? There's so much to be done there. You saw Hubble image an extrasolar planet as a little dot of light. That's awesome, but there's only so much we can do with that. Now, we may not be able to see extrasolar planets nearly like we do those in our own solar system, but James Webb will enable us to go that much further, take that next step, study them better, study them distinct and isolated from their stars. And even, again, in number 4 there, you see study how planetary systems change over time. Are there worlds out there like Earth? We don't know. There's an awful lot of planets out there. James Webb will help us to examine them and analyze them and see how friendly they may be. So again, great goals. You may have heard James Webb has been delayed more than once, several times. It's currently slated for launch in 2021. The telescope will need to be checked out, of course. Until then, we still have Hubble, and it's still doing a fantastic job. So I think a great big thank you is due to the Hubble Space Telescope, and I'd like to thank you for being with us tonight. Hope you've enjoyed our little journey there, giving you a lot to think about and consider. I'll take a few questions. Before we do that, I want to just advise you that I will be back on July 20th, 2019. You might recognize that as a very special date. That will be the 50th anniversary of the first manned landing on the moon. What a historic event that will be. I'm sure you'll hear about it as we get closer, but I've planned a presentation for you, Reach for the Moon, and we will be in a larger venue. As a reminder, we'll be again in the SRC 2000 location here at College of DuPage. So I hope you'll come back for that. And one other quick reminder that, as you know, I have other courses and lectures out on YouTube. You can go out and learn all about stars and galaxies. You can learn about the solar system. So you're welcome to go out and do that. At this time, I'd be glad to take any questions you might have. We're going to have a couple of microphones, I think. So I'll be glad to entertain any questions you might have. There's our first one.
Has Hubble discovered any suns in any of those galaxies?
So if I understand your question, has Hubble discovered other suns in other galaxies? Stars, of course, are suns. And interestingly, Hubble can give us, again, our best views of individual stars and do a tremendous amount of research on those particular objects. But I'll just add to my answer there that Hubble just recently imaged the Andromeda galaxy, M31. Many of you have heard of that, seen that. And also now just recently released the M33, or what they call the Triangulum galaxy. We can see individual stars in those galaxies. Again, an unprecedented capability that Hubble can do. Does that answer the question? Okay. I saw a hand over here.
Why did they name it James Webb? Some of us don't know who that.
So James Webb.
What that is.
Why the new telescope we named James Webb? James Webb was the major administrator. He was the NASA administrator during the 1960s during the moon landing. And he's given a lot of credit for the success of that program, so thus NASA has chosen to name the telescope the James Webb Telescope.
Wouldn't the stars from the Pillars of Creation picture have already been made, since it takes an amount of time for the light to travel, like, to the stars to take the picture?
That is a good question. Those stars are some thousands of light years away. Haven't they formed already? The short answer is yes. Understand a couple of things. Number one, star formation takes some time. It does take many thousands of years. I'll just pick a number. Let's just say 1 million years for a star to form. Okay, 1,000 million. And it's true those things are several thousand light years away. So they might not be all the way formed, but they are more formed today than they appear to us, I think is your question. So good question. Thank you.
So when Hubble goes around Earth, when it orbits it, does it travel at the same speed when Earth rotates?
That's a good question. How does Hubble orbit Earth? Hubble orbits about 340 miles up. It's traveling at about 17,000 miles an hour. So that is much faster than Earth rotates, of course. There are satellites, I think you're referring to, that we can put in the right position, right distance, that do orbit in the same time Earth turns, but not Hubble. Hubble was placed in an orbit for a couple of reasons. Number one, that's as high as the space shuttle can go to launch it, and that's as high as the space shuttle can go to service it. So when the astronauts went up to service it, they had to take extra effort to get up and service. So it is in a lower Earth orbit. Good question.
Do those are they identified what that material is by those colors?
Yes, when we see colors in various pictures, they often can indicate different elements. As you said, in the planetary nebulae, that is correct. We can identify certain wavelengths of light that are given off by certain elements, and we can identify a certain element using spectroscopy to do that.
One other question. When the guy had the screwdriver, why did the screw turn and not him?
So that's a good question. When they were servicing Hubble, he said when he turned the screwdriver, why didn't he turn? They thought of that. They thought of that. Tremendous. I can't tell you the effort and time that went into thought before the mission. You saw them swimming around in the pool practicing literally every move. And I mean literally every move. You will take the screwdriver and you'll move it 18 inches, and you'll do this, and you'll do that. And every little move, put your foot over here, was choreographed, rehearsed, practiced, because they had one chance at this. They didn't want any surprises. They still got a few, but the point was he was well anchored. He was well anchored. You might have heard them mention for the one astronaut, Megan MacArthur, to move the arm. The Space Shuttle has a robotic arm, and the astronaut can put his feet in there and be held securely while they're working on Hubble. So good question.
Considering the James Webb Telescope is beyond revolutionary, can you explain to me why it's taking 10 years? It just doesn't make sense. There has to be something more than just the equipment issues or research and development, because so many of us are waiting for this spectacular next generation. I was wondering, what is it politics, money, government, or something else?
Sounds like you've all answered that for your own self. Yeah, I haven't studied the question in detail. Astronomers have been very frustrated with the delays of James Webb, as the public has been. James Webb is far over budget. James Webb is far behind schedule. Ultimately, I think it's fair to say, it's my opinion, that it's probably at a point where it's too late to cancel it. You've already invested so much, you now have to see it through. NASA, I'm sure, is as frustrated as anybody. There have been unprecedented challenges with this cutting-edge technology. Is it possible it was a little bit beyond us 10 years ago? Yeah, we've worked through a lot of that, and we're just so close now. But what I understand is there's just exhaustive testing, because we will not get to service it. And so anytime a test turns up any problem, they stop. They don't press forward. So I don't have the precise answer for you, but I think we all feel your frustration.
You had discussed the Andromeda Galaxy, and apparently the Milky Way is going to cross the Andromeda Galaxy some 5 billion years from now. Is there a good system of calculation of what's going to happen to, quote, Earth, when we're talking about that sort of thing?
So yes, Hubble's been used to observe the Andromeda Galaxy. And I keep saying this, but here's again where Hubble shines. Its positioning is so exquisite that it was the first telescope to be able to measure the motions of stars in the Andromeda Galaxy. And they measured a number of those, and using that, first uncovered the idea that Andromeda is approaching the Milky Way. There's going to be an interaction. Now, just recently, the Europeans launched a mission called the Gaia mission, and it was specifically designed for this, among other things. It has mapped the sky to such ultimate precision, and when it mapped the Andromeda Galaxy, it got an even better precision to those measurements, and we now do have a little better idea. It's going to be something similar like this. We have the Milky Way over here. It's not a very good Milky Way, is it? And Andromeda over here. It's going to be kind of one of these things where they kind of go like this. Okay, and as we get closer and closer, it's harder and harder to be precise, but the point is we have a better, kind of a second estimate or second version of what's going to happen. It now looks like it will not necessarily be a head-on collision, but it'll be more of a glancing blow is kind of the way it looks. The reason for some of the uncertainty is we actually have another third galaxy out here called the Triangulum Galaxy, and it's even less precise on what it's going to do. This is cutting-edge stuff. So the short answer, I think, is that yes, Hubble's been used for that. Number two, we have better data just that we've got brought down from the European satellite, but this third galaxy has made it difficult for us to be extremely precise on the exact nature. As far as our sun, again, there's any number of things that could happen. It's very, very extremely unlikely that any stars will collide. There may be a few. Some stars could be ejected outward of the galaxies, but ultimately we think it likely that two galaxies may eventually merge together.
I had kind of a three-part question. I was wondering how long it took to build the Hubble, how much it cost, and then how much longer they think it'll be operable.
Good questions. Looking back, it seems like a bargain, even though we had some problems with it ultimately. You got to put yourself back, of course, way back into the 1970s, 1980s. Hubble was going to be launched in the late 1980s. It didn't make it to orbit until 1990. So Hubble took, approximately, I'm just going to use a round number, 5 years to design, develop, build, test before it was launched. And how long does it have to go? It's doing well right now. They've learned a lot about it, obviously, over the years, how best to treat it and take care of it, and the care and feeding, I guess. But the point is that they, again, are trying to get as much science as you can out of it, but at the same time take good care of it. Right now, it's in very good health. It should go several more years, we think, at least. So I'll have to come back, I guess.
In looking at the images and interpreting them in terms of color, perhaps being a representation of heat or energy or mass, how does it get interpreted when you take into account blue shifts and red shifts due to speed?
Okay, good question. So I was referring to what's called the Doppler shift. Maybe many of you are familiar with that. In other words, we receive light from any object out in space. We need to analyze it, don't we? Because I alluded to the fact that it tells us something about temperature. What he's alluding to, again, many of you know the Doppler effect talks about the speed, velocity of an object. There's kind of at least two different factors here, isn't there? So a body, when we take its light and break it into a spectrum, will show us, I'm just going to use a very simple general example here, a spectrum that looks like this when we talk about the intensity of the light and the wavelength of the light. And this curve gives us a pretty good idea of the temperature of the star. How do we know that? Well, wherever the object's giving off the most intense light, whatever wavelength that might be, we can take that and plug it into an equation and find the temperature of it. We've tested this on Earth. We can do it in the laboratory. Heat up gas to a known temperature, look at the light and say, oh, sure, it tells us, it shows us this, and this particular spectrum is telling us the temperature. Okay, it's called Wien's law. My students are going to learn all about it real soon here. So number one, that's temperature. But on the other hand, let's say that we look out in space and we see a star like that, and let's just, for the moment, keep it simple. Let's say it's an identical star. We see something very similar, but we notice that that star looks more like that. And we say, well, now that's interesting. We would have thought it would be a little different temperature, but gee, they sure look like identical stars. What may well be happening is this star's wavelength here is shifted a little because, as you mentioned, the Doppler shift. So astronomers have to take some effort to kind of untangle the two and separate them and say, no, one is temperature and one is velocity. And we have ways to do that. How do we do that? Because in many, many objects, we don't just have a simple spectrum like this. We can break the light into a spectrum that only has certain particular wavelengths to it. And when we look at those two stars, if that's star number one, star number two will have the very same wavelengths, but again, all shifted. And so you say, well, it is the same star, it is the same elements, it is the same temperature, but it's shifted. So in other words, we have to untangle the two effects. It was a long answer, I know, but did that answer your question? Okay, thank you. Quick course in spectroscopy, I guess. Is there another hand here?
Did James Webb have a part in creating the Hubble Space Telescope?
No, he did not. He had a big part in getting astronauts to the moon, though. So James Webb was, again, a very effective administrator during some very challenging times there in the 1960s. We look back and we applaud the Apollo mission, but boy, I can't tell you the time and effort and energy that went into getting our astronauts to the moon. So the question was, is there a certain budget or operating expense to keep the Space Telescope operating this year? Yes, indeed there is. It's part of the NASA budget. I don't know the exact number, but I can assure you that astronomers all vote for that budget. Don't touch that. If there's one telescope we love, it's that one. So yeah, good question. There's a hand over here. Let's get the microphone over there so we can all hear it.
Yes, in the other house. I was curious, how come we didn't build another Hubble Space Telescope? You know, just take the same plans and shoot another one up in space.
That's a good question, I guess. Why not just duplicate it? I would think the answer would be because we felt we could do better. If Hubble could do this, boy, let's build the next better one. Because, you know, you think of Hubble, obviously was unique in being one of the first major space telescopes, but why not, again, build a better one? And that might come back to our question about James Webb Space Telescope. Did we maybe take off a little more than we could handle? Maybe. I'm not probably qualified to judge that, but that's probably the answer why we didn't just build a duplicate. Yeah, let's build a better one. Anything else? There's one here. Another hand over here. You guys got good questions tonight.
So is the James Webb Telescope going to be in orbit of another planet in our solar system, or is it just going to be hanging out there?
It's going to just be hanging out there at the L2 point. And we are, again, as I mentioned, I think NASA's taken every pain to make sure it is as perfect as we can get it, to ensure its longevity. Because again, at this point at least, I'll qualify that, there are no plans to be able to service it. You say, well, wait a minute, I thought that we're going to build a new spacecraft and rocket on, we could go out past the Earth. That's true, but the telescope's not designed to be serviced. So again, we hope we get it right. Okay, down here in front. So any other telescopes comparable to Hubble, each one is designed for a specific niche, so to speak. Hubble, of course, was the first large space telescope, and it was optimized, as I said, for visible light, but also a little bit of infrared, a little bit of ultraviolet, and it's good at a lot of things. Some of you, I think, have heard my other lecture on the Spitzer Space Telescope. That's a smaller telescope optimized for infrared astronomy, and it's done a magnificent job. It's often overlooked. That's why I lectured on it, because it has shown us so much. There have been ultraviolet telescopes. NASA currently has X-ray telescopes, gamma-ray telescopes in orbit. They each have their own niche. We could each spend an hour or so talking about each one of those. Each reveals a different view of the universe. Astronomers learn so much when we look at an object, not just in visible light, but let's see what it looks like in infrared. Let's see what it looks like in ultraviolet, even X-rays or gamma rays in some cases. These are more specialized niches, but we do have a suite, so to speak, of space telescopes covering all the different wavelengths. Yeah, L2 is just a shorthand for something called the Lagrangian point. If you go way back, what's his full name? French mathematician named Joseph Lagrange. I think I'm saying this wrong. Apologies to anyone out there. But he said, you know, there's several points around the Earth where the gravity of the Sun and the Earth would all balance, and you could basically float, at least theoretically. So that's just point number 2. There's one between the Earth and the Sun. There's one ahead of the Earth, and there's one behind the Earth. So if you go home and look up the Lagrange points. Okay, another hand over there? Sure.
I have a question about when the galaxies collide.
Okay.
Now, I'm guessing that they would be speeding up as they're doing this. And are we talking billions of years for them to pass each other, or hundreds of millions?
Okay, so good question. The short answer is there's a great variety of things that can happen. I probably should have added a few animations here. I could probably pull one up if you'd like to hang on a second. But the short answer is that different galaxies are going to come in at different velocities. You notice what's on my background here, huh? What have I been thinking about for a few weeks, right? Different galaxies are going to come in at different velocities, different distances, and they're going to impact perhaps at different velocities, again, distances. They're going to have different amounts of matter. Let me go ahead and pull up, let's see, that one, I think. And they're going to have different effects. Some may just move through each other slowly, some more quickly, and they're going to have, again, different effects. Let's see if this is where I want to show you guys, okay? So there's a great variety. There's no one simple thing. Let's see if that'll work for me. Share with you one of the animations from one of my classroom lectures. Let's not play the game though, shall we? So here you've got, for example, 2 small spiral galaxies. And these are just real simple early animations. I just grabbed them because they're... And as they move through each other, they move slowly and they have a head-on impact. They have a tremendous effect on each other. Notice that? They basically destroy each other before merging. Notice the tails flung out into space. I said earlier, if we model it just right, we can simulate what we actually see in space. How about that? In other words, that's a real picture, and you just saw an animation that's pretty close to showing how it came about. So again, two small galaxies, spirals here, head-on impact at a relatively low velocity. There's a big mess. They merge, and they fling out these streamers of stars. Okay? I'm sorry if you can't see that so well. But let's go back now just briefly to show you a little different example of a little different simulation. Here we're going to have a small elliptical and a large spiral. Who do you think is going to win that battle? Okay, here comes our elliptical. It's going to punch a hole right through the center of the big spiral. Notice the different colors indicating, again, temperatures and ages and masses. Gravity will initiate a ring spreading outward within the spiral. Look at the elliptical dissipating. It's stripped of stars. But notice our spiral ends up with this very unique, interesting ring, and sure enough, we found one. We found one that matches what we've simulated. So you see a second example? I'll bet you want one more, don't you? Okay. I'm sorry, I didn't let you watch the end of that. Let's go back. Now we'll turn the tables. We're going to have a large elliptical, small spiral. Who do you think wins that one? Before I show you this one, remember ellipticals generally are not going to have much gas and dust. They're going to be a large, roughly spherical galaxy, kind of that cooler, yellowish, older stars. Whereas our spiral, on the other hand, is going to have more of the bluish stars, more gas, more dust. Let's see what happens when the little spiral interacts with the huge elliptical. Of course, the spiral is shredded. The elliptical is going to pull a lot of the stars back in. And if we, again, get to the right perspective, you know what's coming. We have found one that looks a lot like this. There's an example where an elliptical, we think, has basically cannibalized a spiral. And so you say, and it's an elliptical, why does it have dust? Well, that's what's left of the spiral. So hope you didn't mind, but I wanted to show you some examples of what I've been describing all along. Oh, I'm sorry, we can go down here first. Sure. I missed you earlier. Go ahead.
How do they schedule what the Hubble sees?
How do you schedule Hubble? You guys want to take a picture? Get in line. So Hubble's handled like all major professional observatories. Basically, as an astronomer, I would write a proposal and say, well, I want to observe this with Hubble. Now, Hubble being so unique, the very first hurdle is to say, why do you need Hubble? Why can't you go to Palomar or Kitt Peak or Mauna Kea or go to Keck or go to wherever and do that on Earth? You want to take a pretty picture? Go do this, go do that. You want to measure that? You don't need Hubble. So that's the first hurdle. And there's a committee of astronomers who meet regularly to consider these proposals. So that's that first jump. You say, well, no, you just go use another telescope. Yours can only be done with Hubble. Okay, we'll consider it. So there's a number of factors you can imagine, the scientific merit, the scientific probability of success. I want to do this with it. Well, you're probably not going to succeed, most of us don't think, so we don't know that we want to give you time. But this sounds like a very promising approach. And is it, again, a topic that is of interest to many astronomers, or is it just your one little pet project? So there's a number of things. Once you pass that hurdle, and they say, okay, we decided we're going to give you, whatever it is. Most observatories on Earth, they give you by night or half a night. So you can have 3 nights at the Keck telescope. Well, on Hubble, it's more hours or orbits. We'll give you 20 orbits because you need this, 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 and we're going to point the telescope. But then there's a master schedule, you can imagine. We're not going to swing Hubble all over the sky looking at things, okay? Hubble moves very slowly, so it's more like this. Today's schedule for you is to shoot that one, and then shoot that one, and then that one, and then that one, and then that one. So they plan it out very efficiently, what Hubble's going to do, how many orbits, what instrument you use, because to switch instruments takes a little bit of time and effort. So if you say, well, I want to take visible light pictures, and you say, well, I want to take ultraviolet pictures, well, we're going to finish up the visible first, and we'll switch the telescope over to ultraviolet. We'll take yours, and we'll take some other ultraviolets. Then we'll go back to this, and so on and so forth. So you can see there's a lot of factors. Currently, the subscription rate is about 1 out of 5 proposals makes it, 20%. So often if you really, really need Hubble, you'll get back in line again and ask again. That's kind of how that goes. So good question, interesting question. So the question was Hubble ever designed to come back down or be brought back down? Maybe put in a museum or something, that'd be cool. Let me answer that first and I'll make sure I got the rest of the question. Originally there was thought of that back in the early days, but understand that Hubble was designed, again, to take advantage of the space shuttle. So they said, so the space shuttle can lift this much to orbit and this altitude orbit. We're going to build it as big as we can get it and still make that with safety margins. When they started doing the math and saying to bring it down would be a whole different ballgame from what the astronauts normally do in landing the space shuttle. When the space shuttle comes down, it has a certain weight. The astronauts are trained to fly that vehicle down. You're talking a whole different thing here, 25,000 more pounds. There was still a little thought in the early days, but after the Challenger disaster, when the Challenger space shuttle was lost and the Columbia was lost, they said, no way are we going to try something like that. It's just too dangerous for our astronauts in the space shuttle. So that was kind of that. The other part of the question was the soft docking. You saw them put that little fixture on there. They kind of know that sooner or later it's going to have to come down. Yeah, NASA's just sort of quietly working on what that'll be. There had been an idea, you know, when they were not going to send the astronauts back, could we send a robot up to work on Hubble? And they said, that is way too complex. Again, our astronauts did just a superb job, you know, but they were highly trained, and I mean highly trained, intelligent astronauts. So the short answer is, yeah, they're working on that, and when that day comes, they'll say, we're going to send this little rocket up and grab Hubble and steer it down.
I'm always wondering about stability. Now, I understand it has gyroscopes, but in order to be perfectly still, especially for deep field exposure, over that much time, to be that precisely still, whatever that means, how is that accomplished? Or how is it even calibrated?
So we're talking about Hubble's pointing capability. It's a big question. You're exactly right. If you have the best telescope ever made, most exquisite telescope, it's in space, no atmosphere to blur it, how do you hold it steady? Especially as it passes into the sunlight, gets heated up to 200 degrees, passes into the darkness, minus 200 degrees. Things expand, they heat up, they twist, they turn. So it started with, before launch, astronomers mapped the sky to an unprecedented level to get what they called the guide stars. We mapped the sky for you astronomers out there down to like 15th magnitude, because they knew that Hubble would need to lock onto a star and say, that's the star I'm going to hold on to. Second of all, you can't fire thrusters to stabilize this spacecraft because you'll contaminate the optics in the instruments, so it's not going to be a chemical thing. So they came up with, as you said, gyroscopes or reaction wheels. You power up the wheel and it spins this way, and somebody said this earlier, well, that would make the telescope spin the other way. Those had to be exquisite, and that's why they failed. They were such exquisitely delicate instruments that they would eventually fail and had to be replaced. Now, of course, they learned how to improve them, and when they put the new ones in, they were better. Okay, so all those kind of things had to be taken into account, and at this point, I think they got it to that point in that 2009 Service Mission 4 that they said, this is it, this thing has to be extremely robust. Even the solar panels, when they would pass into the sunlight, the early versions would kind of flutter a little bit. And they said, no, we're going to have to change that, so the astronauts changed the solar panels. So that's why we say Hubble's the best it's ever been. Hubble's the best it's ever been, and took a lot to get it there. Let's do this. The questions keep coming, but how about if you have remaining questions, come on down front. The rest of you, have a great evening. Thank you again for being with us.